Analytical Chemistry 1, Lesson 54. Now, the last major topic for our course is that of electrochemistry. We are particularly interested in how electrochemistry could be used for chemical analysis. Electrochemical methods can be used to produce energy, in care of a battery or a fuel cell, and it can be used to refine materials. Many metals are refined from their ores electrochemically. They also produce new materials and new uses for materials such as thin metal protective films. In this first lesson, we just want to go over some of the basics of electricity. Some of the most fundamental properties of matter are mass and charge. Mass responds to the gravitational force, and electric charge responds to the electromagnetic force, two of the four fundamental forces in nature. Gravitational forces are only attractive. There's only one kind of mass. But electromagnetic forces can be either attractive or repulsive, so there are two kinds of electric charge. We have chosen to call them positive and negative. And as you've learned before, opposite charges attract each other, while like charges are repelled from each other. Objects that possess either or both of these properties move in response to fields. An object with mass in a gravitational field moves from a region of high potential energy to a region of low potential energy. Similarly, an object with electric charge moves in an electric field from a region of high potential to a region of low potential energy. The most common fundamental particle with negative charge is the electron, and the most common fundamental particle with positive charge is the proton. We've come to understand that the proton is actually made up of still more fundamental particles known as quarks. Their energy, however, places them way outside the realm of chemical interactions. There are other electron-like particles, leptons, such as muons and tau particles, and there's antiprotons with a negative charge and anti-electrons, also known as positrons with positive charge. The way they can contribute to chemistry is really left for another course. So for chemistry in this course, we focus on protons and electrons. There are, of course, also neutrons which do not have an electric charge, like the proton and neutron. Electron, they do respond to a gravitational field, but they do not respond to an electrostatic field. We've already learned that the nucleus of atoms consists of protons and neutrons. They have much more mass than electrons. Electrons are in motion around atomic nuclei and can move through assemblages of groups of atoms we call molecules. Chemical bonding arises from the redistribution of electrons. Chemical change arises when atoms and molecules move from one region to another. Nuclei and electrons together move to establish the lowest potential energy configuration possible given the constraints of the system. Electrochemistry develops methods and instruments to measure and control the exchange of electrons, which is at the heart of so much chemistry. One of the ways we try to control the flow of electrons is by using an electric circuit. The basic parts of an electric circuit include a closed path for the electric charge carriers to move around, a device of some design that creates a potential difference that drives the charge carriers in their motion around the circuit, some kind of resistance to the flow of charge, some kind of capacitance that can store electric charge and electric energy, some kind of inductance that opposes changes in the flow of charge and stores magnetic energy. Every electrical circuit possesses these properties. Sometimes it's by design in the explicit inclusion of discrete components, but if not included explicitly, there is always unavoidably these properties present to a greater or lesser degree. In particular, the capacitance and inductance are related to changes in the flow of current around the circuit. Because a lot of our interest involves steady state, and by that I mean not changing current flow situations, we start by ignoring the capacitance and inductance. So we're left with a voltage source and resistance. So what is this green box? Well, the voltage source is possibly many things. What is important is that it establishes a potential difference between one side of the device and the other, and it makes it difficult, and in the limit it makes it impossible, for the electrons to go from the high potential region to the low potential region through the device. Instead, they must flow through the circuit, passing through the various elements, in this case it is the resistor, and finally reach the region of low potential energy. The device in the green box tries to maintain this potential difference as long as it can. The green box might be an electric generator such as found at a power plant. A hydroelectric plant converts work done by water falling through a gravitational potential and uses that work to drive a generator that creates the electrostatic potential difference. It might be a nuclear reactor, which is where it uses the heat from the nuclear reactor to boil water and uses the steam to drive a generator to create the same potential difference. And maybe it's just a hamster on a hamster wheel driving a generator. Well, in any case, work in one form is used to establish the electrostatic potential difference. Closer to our chemical home, however, the potential might be created by assembling some chemicals in such a manner that the electrons would like to move from one set of reactants to another, but because of the design of our device, the only way they can move is through the external circuit. Work was done somewhere to make those chemicals, and now we can harness that work in our electric circuit. Now that device, of course, is called a battery. This takes chemical potential energy and converts it into electrical energy. Chemistry can produce electricity, and electricity can be used to drive chemistry. Electricity was discovered well before electrons and protons. In trying to understand it, scientists made some assumptions that have become conventions that are still hang around and shape some of the language. Early scientists knew of charge and ended up measuring its magnitude in units of coulombs. Only later did they realize that charge was discrete, little tiny packets of charge. The relationship between these quantized units of charge and the continuous concept previously held was developed. The constant connecting the two has come to be known as the Faraday Constant, with the value of 96,495.34 coulombs per mole of charge carriers. A mole of these discrete units of charge corresponds to this amount of coulombs of charge. This can be applied to positive or negative charge carriers. In this equation, Q is the commonly used symbol for charge and N is the amount of carriers measured in moles. In an electric circuit, as long as the resistance is not infinite, there is a continuous flow of charge from high to low potential energy. This flow is called a current. In a circuit such as the one shown here with just a single path, the current must be the same everywhere at the same time. If not, charge would be building up somewhere and decreasing elsewhere. The conservation of charge requires that the current be the same everywhere. Current is measured in units of ampere and is the amount of charge in coulombs passing a point in the circuit per second. Now here's the relationship. Remember that time must be measured in seconds and charge in coulombs for the current to be given in amperes, or colloquially amps. You will see the symbol for current as both a capital and a lowercase letter I. While units have a defined usage of upper and lower case, variable symbols less so. Each author will choose symbols as is most convenient, but it is most common for people to use I. If you see it both ways, do not be distressed. The difference in electrical potential is the key to having a current of charges flow around the circuit. If there was no difference in potential, no current would flow. When a charged particle moves between 2 points of differing potential, energy is released if it is going from high to low potential. And if we have a device that pushes the charged particles in the other direction, energy has to be injected into the system in the form of work. The potential difference is measured in units of volts. We often use E as a symbol for this electric potential difference. When a charge in coulombs moves through a potential difference, the energy released or absorbed is measured in joules. It is also common for the potential difference to use the symbol V as well as reporting it in value in units of volts, which also has the symbol V. Now, an important electric circuit equation is known as Ohm's law. It relates a voltage difference, a current, and the circuit resistance. Another useful property of electric circuits is known as power. This is the rate at which work is done. It is work divided by time. When work is measured in joules and time in seconds, the power is in units of watts. We've introduced 8 different variables here with which an electric circuit can be analyzed. One additional correlation needs to be made. We learned in Chem 1050 that work is the energy change in a system. Work done on the system by some external force is an increase in the system's energy. Work done by the system on the surroundings means the system gives up some of its energy to provide work externally. We learned then that changes in Gibbs energy was the work on or by a system that was any kind of work that was not pressure volume work. So in our electrical system, Gibbs energy changes are the electrical work arising in our electric circuit. In electrochemistry, we usually combine this with the first expression involving the Faraday constant. This relates a potential difference to the change in Gibbs energy. Here is another important concept to appreciate. We know that the magnitude of the current that flows around the circuit is given by the equation I equals Q over T. But which way does it flow around the circuit, and does that question even matter? Well, in the early days, they could only make assumptions, and they chose a convention that envisaged a positive charge carrier moving from the positively charged region of the voltage source to its negatively charged region. Something for it was moving from a region of high potential energy to a region of lower potential energy. A positively charged entity would be attracted to a region that was more negatively charged. In a circuit such as we have modeled here, with the idea that the components are connected by metallic wires, we have since learned that in fact it is negatively charged electrons that move around the circuit in the opposite direction. Because of their charge, they are still moving from a region of high potential energy to low potential energy, from their perspective. Many of the properties that we want to measure do not change from this difference. The current, the power, the work, they all come out the same by changing the sign of the carrier and the direction of its flow. Because of this, electrons and much of the electrical industry, electricians and much of the electrical industry, continue to follow the convention of current flowing from positive to negative. And they do just fine with that. And we too will learn to interpret current flow under different conditions as being either negatively or positively charged carriers moving in opposite directions as driven by the differences in electrostatic potential energy created by the device in the green box. There are two important tools that we use in analyzing electric circuits, an ammeter and a voltmeter. They are used to measure respectively the circuit current and the voltage drop across a section of that current. An ammeter is a low impedance device. It has very small internal resistance. It is designed to minimize its effect on the circuit it is analyzing. You place it into the circuit. It doesn't matter where you position it, for the current is constant throughout the circuit. If you have a circuit with parallel paths, the current is constant in each leg of the circuit, and they likely are different. The ammeter can be used to measure each leg separately if properly positioned. Connect the positive terminal of the ammeter to the positive side of the circuit. Connect the negative terminal to the negative side of the circuit. The positive terminal is commonly colored red. The negative terminal is commonly colored black. In addition, it's sometimes labeled as common or just COM or even ground. And you do have to break a circuit in order to insert an ammeter. But once installed, you can then turn on the circuit. If the measured current is negative, you have connected the circuit incorrectly. Switch around the terminals. A voltmeter is a high impedance device. It too is designed to minimally disturb the circuit it is analyzing. While an ammeter might have an internal resistance of 1 ohm, a voltmeter might have an internal resistance of 10 to the 12 ohms or even higher. Every part of the circuit that has a non-zero resistance will show a drop in the potential across it. As with the ammeter, connect the positive terminal to the positive side of the circuit, similarly with the negative terminal. They are again usually colored red and black respectively, with the negative terminal also labeled the common terminal. When connected correctly, you will measure a positive voltage. If negative, you have it backwards. If the voltage source does not have its output labeled, using a voltmeter in this manner can determine it. If the measured voltage is positive, then the red terminal is connected to the positive or high potential energy side of the voltage source. Now, this is using the convention that current flow is of positively charged particles. But in electrochemistry, we have to worry about where the electrons are because the chemistry involved depends upon them. In the next lesson, we will look at electric circuits and electrochemical processes.